In the previous lesson, you learned about two different types of changes. Physical changes, where the bonds between atoms do not change even though some external change happens to the matter, and chemical changes. And in a chemical change, the bonds between the atoms change during a reaction. In this lesson, we're going to be learning how chemical formulas or chemical equations describe matter and they describe those chemical changes. Let's get started on our lesson about chemical formulas. And first, we need to define what a chemical formula is, and then we're also going to define what a chemical equation is. A chemical formula shows the makeup of substances, what the atoms are that are present, how many of each kind of atom, using symbols, coefficients, and subscripts. So the symbols tell us what atoms are there, coefficients tell us something about the number of units of those atoms, and subscripts tell us something about the number of atoms. Let's take a look at an example. Here we're going to use an example of a substance called nicotine. Nicotine has a very specific chemical formula. And what's pictured here is not a chemical equation. Okay, a chemical equation has to have two sides, a beginning and an end. This is a chemical formula. It tells you how one substance is made up. In this case, we have the chemical formula C10H14N2. Now, what does all that mean? Well, C10, that little subscript 10, tells you that there are 10 atoms of whatever the symbol is before. In this case, it's 10 atoms of carbon. And that's what a subscript is. It's a small offset number next to an atomic symbol, and it tells you how many of each kind of atom is in the molecule or the crystal unit. In this case, we have 10 carbon atoms because it always follows the atom. The subscripts always follow the atom that they're identifying. There are 10 carbon atoms in a nicotine molecule. Hydrogen, notice, has a subscript 14, and that means there are 14 hydrogen atoms in a nicotine molecule. And nitrogen has a subscript 2, so there's going to be fewer of those, just 2 nitrogen atoms. Each of these carbons is going to have 4 electrons in its outer shell. You could probably have guessed that from where it is on the periodic table. Each hydrogen has 1 electron in its outer shell, and each nitrogen has 5. And we know from previous work that we've done that every atom wants to have a stable outer shell, and that means either 2 electrons in the outer shell for really small atoms like hydrogen, or for most atoms on the periodic table, that means 8 electrons in their outer shell. And because I have a chemical formula for nicotine, I can conclude that there must be a way to bond these atoms together so that they are stable. And sure enough, I can find a way to put all of these atoms together. Now notice what the chemical formula doesn't tell me. It doesn't tell me where the atoms are or which atoms are bonded to which other atoms. It's just an accounting tool. It tells me how many of each atom are there. Now, I'm not going to draw all of the electrons like this every time I make a molecule. When I show a molecule bonded together, I'm usually just going to draw it like this. And we know that there's electrons that are involved in holding the different atoms together. But the real key here is what the chemical formula told us. The chemical formula tells us how many of each kind of atom are in the molecule, and regardless of which way I draw the molecule, I have to have 10 carbons, 14 hydrogens, and 2 nitrogens. And if you wanted to, you can go ahead and count to make sure that those are all there, and you see that in this nicotine molecule, all of those atoms are present. So I've got this chemical formula, and I have the chemical structure down below of the molecule that's represented with this chemical formula. Hey, what would happen if I were to burn nicotine in oxygen? First of all, what is an oxygen molecule? Well, it's O2. The 2 subscript means that I must have 2 atoms of oxygen, and the fact that it's together as a single formula means that they have to be bonded together. This is an oxygen molecule. And now, when I combine nicotine and oxygen, they react to form different substances. In this case, they reacted to form C10H12N2O and water H2O. Notice that I have C10H12N2O, but that O doesn't have a subscript. I've highlighted the place where you would expect to see the subscript, but there is no subscript there. Whenever a symbol in a chemical formula doesn't have a subscript, it simply means that there's only one of that atom, one atom of oxygen here bonded into the molecule. Same is true with H2O. Notice that H2, I have 2 hydrogens. O doesn't have a subscript, so that means that there's just one of them. And then I'm just going to go ahead and put up what I had before and what I had after. Do you see how I had 2 molecules that were distinct molecules? I could identify, count out the atoms in each molecule, and draw the molecule before the reaction. And then a change happened to the bonds between the atoms in those molecules, and I have a different molecule after the reaction. All right, let's take a look at one more example. That was an example that involved a nicotine molecule. Let's take a look at an example now involving crystalline substances like lithium sulfide. Remember, lithium sulfide is an ionic substance. I have a metal and a nonmetal bonded together. So these metal-nonmetal substances are going to make crystals that repeat their structure in all directions. So here I have the chemical formula for lithium sulfide, Li2S. And all this tells me is that for every 2 lithium atoms, I'm going to have, no subscript on the S. That means that there must be just 1 sulfur atom for every 2 lithium atoms. Now, this is Li2S, but notice there's a lot more here than just 2 lithiums and 1 sulfur. Because whenever I have a crystalline chemical formula, it just tells me the ratio, 2 lithiums for every sulfur, 2 lithiums for every sulfur in a repeating pattern in 3 dimensions. That's what I have here. However, I am going to start off with just 1 unit of this to make sense of the chemical equation that I'm going to write based on this. So here I have just 1 unit of Li2S. But again, remember, what this is really telling me is that in my crystal, I have 2 lithium atoms for every sulfur atom. We're actually going to decompose lithium sulfide to make lithium metal and sulfur. And what's that going to look like? Well, lithium metal is just lithium atoms bonded together in a metallic way. So I'm just going to draw 1 lithium atom for now. And sulfur makes molecules that are rings of 8 sulfur atoms, S8. Now, how am I going to make what I have on the right from what I have on the left? Because I just have 1 unit of lithium sulfide on the left. But that's not going to be enough because I need 8 sulfurs to make what's on the right. So what am I going to do? I'm just going to repeat the pattern here 8 times. And to show that I'm repeating a pattern 8 times of 2 lithiums for every sulfur, I'm going to put a coefficient out front. A coefficient tells me how many units of a certain arrangement I have. In this case, I have 8 Li2S's. And that's what this is going to look like. Notice that I have 8 of those original units of Li2S. On the right-hand side, now, I have 1S8. Okay, so I have 8 atoms of sulfur on the left, and I have 8 atoms of sulfur on the right. The sulfur is balanced like it should be. But what about lithium? Lithium, I only have 1 on the right, but I have 16 of them now on the left. So how am I going to make more of them on the right to show that I'm not losing lithium? I can't possibly destroy lithium atoms in this reaction. I have to have the same atoms on the left and the right. They just have to be bonded a different way. Well, I'm going to use a coefficient. What is a coefficient? It's a large number. I'm going to draw in large font before a chemical formula to show how many units of that I have. And lithium's all by itself, so I can just put a 16 in front of it. That shows that I have 16 units of lithium metal all bonded together. And then in front of the sulfur, S8, I'm just going to leave that blank because a blank indicates a 1. And I have 1 molecule of S8. So this is what the chemical reaction looks like. You'll see that I have a certain arrangement of 8 units of lithium sulfide on the left. And then when I react in a certain way, I'm going to decompose it so I have 16 atoms of lithium on the right and 1 unit of sulfur with S8, 8 sulfur atoms bonded together in a ring on the right side of this equation. All right, so now you know what a chemical formula is. Chemical formulas tell us either how a molecule of a substance is made up, what atoms are in it, or it can tell us the ratio of atoms in a crystal. And I can have a repeating amount of the crystal units as long as I have the right ratio of atoms in my crystal. And then a chemical equation puts these chemical formulas together to show how a change happens. And anytime I have a chemical equation, I have to have the same number of atoms before and after the reaction shown by the equation.